Hello everyone. In this lecture, we will continue our discussion on layout planning and design, and we will continue with algorithmic approach for layout design. We will talk about how can we classify these algorithmic approaches. Algorithmic approaches are important because they can be implemented in computers, and it gives us the powers and speed and flexibility of using computers. So we will talk about how can we classify these algorithms, what are the basic data of these algorithms, how they can calculate or compare different layout alternatives with each other, and what are the further classification and representations that are used in these algorithms. So let's get started. Remember, in our previous lecture, we talked about some basic layout planning procedures. For example, Apple's procedure or Reed's procedure, and we also talk about the systematic layout planning procedure, which consists of 10 steps. Okay, so these procedures give you some basic steps that you can follow in constructing the layout, in making layout designs. But in fact, they do not provide you a formal procedure or algorithm. So you cannot implement this directly in a computer because it doesn't provide you every step in detail, and it will not lead you to a certain single layout at the end. It depends on who is following those procedures. It has in its steps, it has some items or some steps which depends on creativity and etc. Okay, so but in order to implement such procedures in computers, we need all the detailed steps. That's why we need some computer-based layout algorithms which includes all the detailed steps. And by having such computer-based algorithms, we will enhance the productivity of the layout planner. We can generate and evaluate a large number of alternatives. We can rapidly perform sensitivity analysis. Sensitivity analysis is especially important because, you know, while we create the basic data of layout planning, what is it? It is either the from-to chart or the activity relationship diagram. If we are using the from-to chart, we need the historical past data, and it is subject to change. And also, if we are using activity relationship charts, you know, we ask several people to construct these charts, and it may be subjective. That's why the activity relationship charts are not certain as well. So we need to make some analysis on these input, so that how does it affect the output, the final layout. Okay, and by the help of computers, we can do this sensitivity analysis easily. But on the other hand, these computer-based layout algorithms cannot replace human judgment and experience. And it means that, okay, even if we use computerized layout algorithms, we still need an expert on this so that it will evaluate the final layout, and it will include some judgment and experience on it, and give the or provide the final layout. We can classify such layout algorithms with respect to different criteria. For example, we can classify the algorithms with respect to the input data that they use. They may use either quantitative data, for example, from two charts, or they can use qualitative data, such as the relationship charts. We can classify them depending on how they represent the layout. Some algorithms represent the layout in a discrete way. In fact, most of them represent in a discrete way. We will talk about this. But on the other hand, some algorithms may represent the layouts in a continuous way. Another classification criteria is the objective function. An algorithm may use an adjacency-based objective or a distance-based objective. Again, we will talk about these in detail in the following slides. Finally, we can classify the algorithms depending on their function. Are they construction algorithms so that they start from scratch and at the end of the algorithm they develop a feasible layout, or they start with an initial layout and they make a re-layout, they improve this initial layout. Okay? So these four are the main criteria for classifying the algorithms. The first one of classification criteria is the type of input data. We said that either it can be quantitative data or qualitative data. And for quantitative data, the main input, the data is summarized then from two charts. Preparing from two charts generally requires more time and effort. Okay? And in order to construct these from two charts, you need the production route data for each product. You need, even if you are producing 1,000 different types of products, you need to collect all the production routes and demands of these products, and then you need to combine them. You need to calculate each transfers between the departments or the machines, and you need to construct this from two charts. The other alternative to this is the qualitative data, which is summarized in a relationship chart, which is represented by key symbols like A meaning absolutely necessary, E means especially important, and etc. And in order to construct such a relationship chart, you may need to talk or survey multiple individuals. And when you talk to these multiple individuals, usually what you will get is inconsistencies. One people will say that, okay, these two departments are absolutely necessary, but the other person may say that they are ordinarily important. Okay, then you need to find a way to deal with these inconsistencies. On the other hand, if you have a from two chart, you can convert this to a relationship chart, or if you have a relationship chart, you can convert this to a from two chart by using some threshold values. Okay, so for example, in order to construct a relationship chart from using a from to chart, what you can do is you can say, okay, if in the from to chart a flow from one department to another is larger than 100, so this 100 is a threshold value that you use. If it is larger than 100, then you can assume it as absolutely necessary. Okay? If it is, for example, between 180, then you say that it's especially important. But it means that you need to determine these threshold values. There are no such certain threshold values. You need to determine those by yourself. Again, in order to convert a relationship chart to a from to chart, again, you may use some weights. Different layout procedures may have their own weights. For example, if you are using ALDEP, ALDEP assigns certain scores to these key values in relationship charts. For example, according to ALDEP, if there is an A relationship between two departments, then its weight is 64. Okay? So you can assign such weights to convert a relationship chart to a from to chart. Another issue or another criteria to classify the algorithms is how can we represent the layouts. Consider this shape. Okay, this shape is a good representation for human beings because we can see this block diagram, we can identify the departments, their borders, and their neighborhoods. But we need to give this representation to the computer so that it can identify, it can understand where each department starts and stops and etc. Okay? So a representation which is convenient for display for human beings may not be well suited for design algorithms, and we need a method to represent this in computers. In order to overcome this problem of representation layouts in computers, most layout algorithms use discrete representation. And in this discrete representation, they use unit area squares. Okay, so this is the layout. So this solid lines shows us the borders of the departments. So what do? We divide the whole area into smaller unit area squares. Okay, so this is one area, this is another unit area, this is another unit area, and etc. And we can represent the departments by such smaller blocks, and we can input these blocks to the computers. We will show you how to do this. And by having these, then the departments are represented by integer multiples of these unit areas. So one department can include, for example, such 5 such unit area squares. So it must be an integer multiple. But then there comes some problems. What is that? Let's consider this. If this department, the actual size of this department is like this, and if we use such a unit area square, then you see that there is a small region over here which does not coincide with the border of the department. And similarly here, you see this small area, it does not coincide with the border of the department. So the main idea in representing with unit area squares is the borders of the department should coincide with the border of the unit areas. Then what can we do? In fact, we make an approximation here, and we just shift this border to left so that it coincides with the border of the unit area. Similarly, we shift this down so that again it coincides. But as you see, from here when we shift it left, we lost some area from this department. Its actual size became smaller. And when we shift this down, then we gain some area and its size became wider. So while doing this shifting of the borders, we try to keep the size of the departments the same as much as possible. But on the other hand, this may lead to deterioration in the shape of the departments. For example, consider this department. It has an L shape in this one, but when we shift these borders up and down, you see now it has a ladder-like structure and it may not be a good representation. In order to resolve this issue, another alternative that you can do is you can use even smaller unit area squares. So the unit area squares here have their own dimensions. Okay, you may assume that, okay, if the total length of this facility is 100, then for example you can divide it into 10 by 10 unit squares, okay? 10 by 10, so that when you have 10 such squares in one dimension, it has 100 length in total. But if you use 10 by 10, then in order to represent 32 dimension here, you see you lose some area. Instead of that, you can use, in fact, 1 by 1 unit area squares. Okay? But in this case, on one side only, you need to have 100 such squares. Instead of 10 squares, you will have 100 squares, right? And this increases this requires more memory in your computers, and the solution time of the algorithms become very large. So you should be careful while dividing these or representing these layouts with unit area squares. The length of each unit area square must be determined in a careful. Representing the layouts with unit area squares by itself does not solve the problem. Assume we represent it with unit area squares, but still we need to input this into computer so that it can modify and manipulate this to improve it or to come up with a better design. Then how we can do it? And in fact, it's easy. Basically, we will give numbers to each unit area square. For example, 1, 1, 1. So this department, this is a single department, and all the unit area, all the squares that represent this department is numbered with this same number. And for this second department, again, we give the same number to each unit area square that's inside this department. And then we just have a matrix, okay, matrix of numbers. And when the computer sees that there are all ones like this, it understands that this is a single department. Again, these twos, again, it understands that this is a department. And the computer now can modify the sequences of these numbers to improve it or to come up with a better design. Another criteria for classifying the algorithms is depends on how we evaluate the layouts, which means that somehow if we have some alternative layouts, or if our algorithm starts with a layout and then improves it, we need to understand whether we improved the layout or not, or we need to be able to distinguish a good layout from a bad layout. Then how can we do? We need to evaluate the layouts, and as we said, we can use qualitative or quantitative criteria to evaluate these layouts. Okay? When we talk about these quantitative criteria, we basically can calculate a score function or a utility for the layouts, and we can choose the layout with a higher score. For example, if we have two layouts, layout Li and layout Lj, and if these layouts have their attributes, for example, the flexibility of a layout, the total flow of a layout, then if we want to compare this layout Li with layout Lj with respect to one of these attributes, then we can calculate a function, and we say that if, for example, fxi is greater than fxj, what does it mean? Basically, if the total flexibility of layout Li is better than the total flexibility of layout Lj, then we prefer layout Li rather than Lj. Okay? This is something like that, and we will talk about some of these score functions. If we are using computers, then using quantitative criteria to evaluate the layouts is preferable. A numerical method is preferable because computers work with numbers. So there are basically two types of objectives, which is the first one is called adjacency-based scoring or objective, and our aim here is to maximize an adjacency score, or we can use a distance-based scoring or objective, in which case we try to minimize the total sum of flows multiplied by distances. The first one of these is the adjacency-based objective, and as we said, we try to maximize this objective. And how do we calculate this adjacency-based objective? Basically, we need to identify, as the name implies, we need to identify the adjacent departments, the departments which are side by side. Okay? And then for adjacent departments, we sum their relationship values. Okay? So for more formally, or in terms of mathematics, if we write it, let M be the total number of departments in our layout, and Fij represent the relationship value, or it can be the flow between department I and J. For example, let's say that department 1 and 2 has an A relationship. Then, using a scoring system, we need to convert this A to a number. As I said, you can assign these numbers by yourself if you are an experienced layout planner, or you can use some predetermined values. For example, if you use ALDEP scoring for an A relationship, you will assign a value of 64. So if department 1 and 2 has an A relationship, and if they are adjacent to each other, then the score that you will assign will be 64. Okay, this Fij represents those numbers, those scores, and Xij is our decision variable, which represents, which takes a value of 1. It's a binary decision variable. If two departments I and J are adjacent in the layout, then it takes the value of 1, otherwise it's 0. Then in order to calculate our adjacency-based scoring, basically we multiply the flow or the relationship between department I and J with this Xij to understand if they are adjacent to each other or not. And we take the summation over all departments, and we want to maximize this value. So as I said, if you have a relationship chart, you need to convert these to numerical values. And in order to convert these, you need to assign values to each relationship value. Okay, so in ALDEP is a layout algorithm that we will talk about its steps later on. ALDEP uses a scoring like this. For an A relationship, it assigns a value of 64. For E, it assigns 16. So in your activity relationship chart, whenever you see an E relationship, you replace it with 16. Again, for important, it uses 4. For ordinary important, it uses 1. For unimportant, it uses 0. And for X, which is undesirable, it uses a penalty. So since it's a penalty, it uses a negative value, and it assigns a very huge penalty for X relationships. Let's make an example to understand how to calculate adjacency-based scoring better. So assume the relationships between 7 departments are given like this. For example, between receiving and milling, so this is department 1 and this is department 2. Between receiving and milling, there's an E relationship. Again, between milling and let's say assembly, then you need to look at the intersection of these two, which is I. There is an important relationship. Okay, so using these relationships, we need and assume that we are given this layout. Now we will calculate the adjacency-based scoring. The first step is to identify which departments are adjacent to which other, and then we will write their relationship values for adjacent departments. So let's look at this shape. Department 3. So we see that department 3 is adjacent with department 7 because they share a common side, okay, common edge. And what is the relationship between department 3 and 7? So this is department 3 and this is department 7, and their intersection is U. Okay, so we write a U here. These are adjacent and their relationship is U. Again, similarly, 3 and 6, they are also adjacent because they share a common side, and we look their relationship. This is 3, this is 6, and the intersection is O. So it's ordinary important. 6 and 7, they are adjacent because they share a common side, and 6 and 7 has an E relationship. So we place an E to this adjacency. But be careful. Adjacency is defined as sharing a common side. Look, department 6 and department 2, are they adjacent to each other? According to our definition, they are not adjacent because they are touching from the corner. They are not sharing a common side. Okay, that's why 6 and 2 are not adjacent to each other. And similarly, 5 and 7 are not adjacent to each other. 2 and 7, 2 and 5, 6 and 5 adjacent, but 5 and 7, 2 and 6, or 2 and 1, these are not adjacent. Similarly, 3 and 2 is not adjacent because they don't share a common side. Okay, so we identify each one of these adjacencies and we write their relationship values on the block diagram. Okay, let's consider another example to calculate adjacency-based scoring. This time, the activity relationship chart is given in this way. We have a block diagram of departments. The layout is given in this way. And this time we are not using the ALDEP scores, but the scores for relationships are given like this. For A, we are going to use 8. For E, we will use 4, and etc. Okay. So how do we calculate the adjacency-based scoring? First, we need to identify which departments are adjacent with each other. And when we look at this layout, we see that department 3 is adjacent with department 1 because they share a common side, common border. Okay, so we go and find their relationship between 1 and 4. Okay, this is 1 and this is 3. Sorry, the intersection is O. So there's an O relationship. So we can write O here. Okay, similarly, department 3 and 7 share a common border, so it means that they are adjacent, and 3 and 7 has a U relationship, so we can write a U here. Okay, now look at here. Department 1 and 7 share a common border here, so which means that these two departments are adjacent as well, and 1 and 7 has a U relationship as given here, so we can write a U here. Department 6 and 7 share a border and their relationship is here, which is E, so we can write E here. Department 1 and 6 share a common border, so they are adjacent, and 1 and 6 has a U relationship as given here, so we can write a U here. 1 and 2 share a common border and their relationship is E. Okay, 2 and 6 share a border here, you see this border here, and 2 and 6 has a relationship of important, so we can write I here. And then 5 and 6 share a common border and their relationship is A. 2 and 5 share a border here, and 2 and 5 intersection is I, is important. Okay. 2 and 4 share a border, and then 2 and 4 has an E relationship, especially important. Okay. And 4 and 5 share a border, and 4 and 5 has a relationship of I is important. Okay, now we identified the relationships, okay, and the adjacencies. Let me delete these extra ones. Okay, and there was a U relationship here as well. Okay, now how do we calculate the adjacency-based score? So we will use basically these numerical values, and we will assign these numerical values to each one of these. So here, this is U, and U is, according to the numerical values, it is 0. Okay, so this is ordinary important, and ordinary important has a value of 1. Okay, U, which is 0, this U is also 0. This E here is 4. Okay, this E here is also 4. This important here is 2, and this is also 2. This A here is 8, and this I here is 2. So basically what we will do, we will calculate the sum of these values. By the way, we have another E here, which is 4. Okay, we will add these values. Okay, so this is 1 plus 4 plus 4. Okay, so 8, 9, and then we will have 2 here, 11, another 2 here, 13, this 2 here, 15, this 8 here, 23, and this 4 here, 27. So 27 is the total adjacency-based scoring if we count the adjacencies only for the 1/2 of the matrix. Okay, we only said that, okay, 1 is adjacent with 3, we counted this one for once. If you do for the whole matrix, then we need to multiply this value by 2 to obtain 54 as the adjacency-based scoring. Okay, so this is how we calculate adjacency-based scoring. It's easy. What are the disadvantages of adjacency-based scoring? First of all, it's very sensitive to the weights that we use. So in the previous example, we used ALDEP scoring, which was assigning, or which assigns an 64 for an A relationship. And we used another scoring, which assigns 8 to an A relationship. And the final layout or the final score depends on what value you assign to these. Okay, so it's very sensitive to the weights, and the layout which is preferable with respect to certain weights may not be preferable with another use of weights. Okay? So the final result will depend on what weights you are using. It's sensitive. Secondly, it disregards the distance or separation between non-adjacent departments. It only looks, okay, if two departments are adjacent to each other or not. If two departments are not adjacent, if they are still very close, if their corners are touching to each other, or if they are very far away from each other, this adjacency-based scoring does not look at it. But in fact, there may be a flow between these non-adjacent departments as well, and if they are closer, then it's a good thing. If they are very far away, then it is worse to have such a layout. But adjacency-based scoring does not give any idea about this. And we can also mention that it is possible to construct two layouts that have identical or similar adjacency scores but different travel distances in terms of paths and flows. Okay, so which one is better? Of course, according to adjacency-based scoring, they are identical. But when you consider the total travel, which is very important, then one of them will be better than the other one. So adjacency-based scoring does not consider this, but still it's very helpful, and some algorithms use adjacency-based scoring for evaluating the alternative layout. The second method that we can use instead of adjacency-based scoring is the distance-based scoring. And in this case, opposite to the adjacency-based scoring, which tries to maximize the adjacency score, we try to minimize the sum of flows multiplied by distances. Okay, so we want to make as minimum travel as possible in distance-based scoring. The objective function is similar to the well-known quadratic assignment problem, in which we try to assign, let's say, a number of machines to a number of alternative positions and then try to minimize the total flow between these machines. Okay? How do we calculate this? Mathematically, we can represent it like this. Again, let M be the number of departments. Fij is the flow from department I to department J. Cij, it is the cost of moving a unit load from department I to J. Okay, cost of moving 1 unit of load for 1 unit of distance. And Dij is the distance from department I to J. Then what do? We multiply the total flow with the cost of flow per distance, and we also multiply this by the distance between two departments I and J. So the adjacency is not important. Whether these departments are adjacent to each other or not, it's not important, but the distance between them is important and the flow between them is important. And we take the summation of this over all departments, and we try to minimize this total flow. And one important aspect or ingredient of this calculation is the distance. How do we calculate the distance between the departments? Generally, rectilinear distances from the centroid of one department to the centroid of the other department is used. Okay, so if you want to calculate the distance between this department and this department, you see they are adjacent, but it's not important again. So we are not saying that the distance is 0. We say that, okay, the centroid of this department is here, and the centroid of this department is here, and basically we use this rectilinear distance between them. Of course, you may use different metrics, or you may try to calculate the actual distance between these two departments, but in most cases we use the centroids and we use the rectilinear distance. So an example will be helpful in understanding. So let's consider this block diagram given here with 4 departments A, B, C, and D. Okay, and the lengths and widths, or the dimensions of the departments, are provided. Now let's first identify the distances. So the distance matrix is given here, but in fact we calculated the distance matrix from this layout. How did we do it? Let's try to understand. Okay, let's try to calculate the distance between department A and department B. Okay. How do we do this? I think the easiest method is to consider like this. Assume this is the coordinate system and this is the coordinate axis. Okay, so this is the origin, which is 0 and 0. Okay, so then identify the centroids of each of these departments. For example, the centroid of this department C, where is it? Since this length is 40, the centroid should be in the middle, so it should be 20. And the distance here again is 20 because it's given here. Okay, so the distance is 20 and the midpoint of that is 10. So the centroid of C is 20, and 10. Okay. And what about the centroid of A? So the length of A is 50, and half of it should be 25. Okay. And the centroid on the center on this side is, this part is 20. Okay, so half of it is 10, but that 10 with respect to the origin, 20 plus 10, it would be 30. Okay, so the centroid of A is 25 and 30. Okay, what about D? Okay, this length here, what should be that length? If you look at the top here, it is 50 plus 30, the total length is 80. Okay, so since we have 40 here, so this side should be 40 as well. And the centroid should be at the midpoint of this. So here the distance is 20. And since we have a 40 here, totally it is 60. Okay, on the x side, it is 60. What about on the y side? So since this length is 20, the midpoint will be 10. Okay, 60 and 10. And finally, what about B? So since this length here is 30, half of it will be 15. Okay, so we have 50 here plus 15 here, which makes 65 on x. And what about on y? So it will be in midpoint here. So the distance here is 10 plus 20, it should be 30. Okay, so we identified the centroids, the coordinates of the centroids. So let me delete the unnecessary parts here. Only we will have the centroids. Okay. So now we can calculate the distances between the departments. So what is the distance, rectilinear distance between A and B? Okay, so we should look from this centroid here to the centroid here. You see their y coordinates are 30. So if you write the formula for rectilinear distance, it will be x coordinate, the difference of the x coordinates plus the difference of the y coordinates. And the difference of the y coordinates is 0. The difference between x coordinates is 65 minus 25, which is 40. So the distance from A to B is 40, as written here. And since it's symmetric from B to A, it's also 40. Right? So what's the distance between A and C? Okay, centroid of A is 25 and 30. Centroid of C is 20 and 10. So the difference in x coordinates is 5. Difference in y coordinates is 20. So the sum of these is 25. Okay, so A and C is 25, and since it's symmetric, C and A is also 25. So you can calculate all these distances in a similar way. Okay, now the distances are given to us. We calculated the distances between the departments. The from to chart is given to us. Okay, it's a part of the question, and it says that from A to B, the total flow is 2, but from B to A, the flow is 1. So you see, this is not symmetric. From A to C, the flow is 4. Okay, so this is given. And also, Cij, the cost of moving 1 unit load from department I to J is also given 1 in this question. And then, how do we calculate the total distance-based score? Basically, we multiply this matrix with this matrix and with 1 term by term. What does it mean term by term? We multiply this 40 with 2 and multiply it with this 1, it makes 80. 25 multiplied by 4 multiplied by 1 makes 100. 55 multiplied by 4 multiplied by 1 makes 220. Okay, so we multiply each term of the first matrix with the same corresponding term of the second matrix, and we multiply it with 1 and we obtain this. If the cost was not 1 but 2, then each value here would be doubled. Okay, so this part here is the total distance times flow. Then we need to take their sum. You can do this either by first taking the sum of each row. The sum of first row is 400. The sum of second row is 180, and etc. Then you take the sum of these rows, which is 120. So this is the final score. Or if you like, you can do this summation using the columns. Okay, you first take the sum of first column, then the second column, the third column, fourth column, and when you add up this, you will find the same result. So we are don't be confused. We are not doing both the row and column at the same time. We either take row sums and take their sum, or we first sum the columns and take their summation. Or basically we are just adding up all these values. Okay, add up all these values and you will end up with this score. Okay, so this is how we calculate the distance-based scores. Of course, there are some disadvantages of this distance-based scoring objective as well. First of all, it assumes that the costs are proportional to the distance between the centroids of the departments, but in fact maybe you are not moving from the centroid of one department to the other. You are moving your storage area of the department can be in one corner, let's say here, and whenever you are moving from A to B, you should move from this corner, let's say, to this corner, not from centroid to centroid, but from one corner to other. But it assumes that the movements are from centroid to centroid. And also, in order to be able to state the cost of moving a 1 unit load from one department to the other, it means that you need to know what kind of material handling system you are using. Okay. So if you are using a conveyor, the cost would be different. If you are using an AGV, the cost would be different, and etc. So it assumes that this material handling system is already known, but in layout planning, maybe the material handling system is determined later on. So we in fact use an estimation of this cost. Okay. On the other hand, if you want to calculate the exact distances between the departments, usually it depends on the aisle layout and the material handling equipment, and also the entrance, the doors of these departments, and etc. Okay, so consider this. If you want to calculate the distance-based scoring or the distance between these two departments, what we do is we basically take this distance. But in fact, if the material handling system, if we are using a unidirectional conveyor which travels in this direction, okay, then it is not possible to move an item directly from here to here. It needs to follow a route, the route of the material handling system, which is like this. You start from here, go to here, then go to here, then go to here, and come here. So it is different than the direct centroid to centroid distance. And on the other hand, if you want to move from this department to this one, and in that case, you need to start from here and then to go here, to go here, to go here, and to return back. But in fact, in distance-based scoring, this is symmetric. Okay, but here you see going from this department to this one has this total distance, which is shorter, but going in the opposite direction has this total distance, which is longer. Final classification of the algorithms depend on whether they are construction type of algorithms or improvement type of algorithms. As we already stated, in construction algorithms, you start from scratch and you determine a layout at the end of this algorithm. The graph-based method that we already talked about is a construction algorithm. Also, we will talk about CoreLab and ALDEP, which are two other algorithms which are construction algorithms. On the other hand, there are some algorithms which are improvement algorithms. They take an initial layout and then improve this initial layout. For example, a pairwise exchange method, which basically exchanges the locations of two departments and tries to improve it, is an improvement algorithm. The craft and MC craft, which we will talk about in following lectures, are also improvement algorithms. So this is the end of this lecture. In this lecture, we have talked about the algorithmic approach for layout planning. We talked about classification of these algorithms. We learned adjacency-based scoring and distance-based scoring, their advantage and disadvantage as well. Okay, we will continue with construction and improvement type algorithms in the following lectures.